Hello, this is module 7. It's about Ethernet switching. Ethernet switching. So Ethernet switching, it's a protocol on a data link layer, on a data link layer or layer 2 of the OSI module. So the module title, Ethernet switching objective, the main objective or the module objective is to explain how Ethernet works in a switched network. So the topics, we have Ethernet frame, explain how Ethernet sublayers are related to the frame field, then describe the Ethernet MAC address, explain how switch builds its MAC address stable, and then for its frame, describe switch forwarding methods and port setting available. So the Ethernet frames. Ethernet operates in data link. So Ethernet, it's a protocol, and it operates at data link layer and physical layer on these two layers. So it is a family of networking technology. That Ethernet, it's a family of the network technology defined by these two standards. The Ethernet and then the wired and then the wireless. So the LAN standard including Ethernet uses two separate sublayers. Those two sublayers, we have what you call link local, logical link control sublayer, logical link control sublayer, and then the MAC. So with logical link controller presses information in the frame, to identify which network layer protocol is used for the frame. Is it IPv4? Is it IPv6 or IPv6? Then MAC sublayer is responsible for data encapsulation and media access. Data encapsulation and then media access, and provides data link layer addressing. So when you look at this, still we have the upper layer, which is the network. So the logical link controller is responsible for identifying, is it IPv4 or it is 6, and then when it comes to this, it is responsible for encapsulation, wrapping. Now the second wrapping the packet by adding the MAC address, that is the frame header, and then a trailer, then together controls the access. So the MAC sublayer is responsible for data encapsulation and accessing the media. Data encapsulation. So with data encapsulation includes the following: Ethernet frame. This is the internal structure of the Ethernet frame. Then we have Ethernet addressing. The Ethernet frame includes both what you call source and destination MAC address. So it's at the data link layer where the source and destination MAC addresses are specified or added onto the package. And once they're added onto the package, it becomes a frame to deliver the Ethernet frame from one network interface card to another network interface card on the same LAN. I've been explaining this on the same LAN. So then lastly, now that they are like this, we expect this is the Ethernet addressing, then this is Ethernet frame, this, and then we have the Ethernet error detection, this part here. So Ethernet error detection, you can call it error detection, includes frame check sequence, which we call a trailer, used for error detection. So media access. So the MAC sublayer include the specification for different Ethernet communication standard over various types of media, including copper and then fiber. So legacy Ethernet using bus topology or hub is a shared half duplex media. So the Ethernet over a half duplex media uses what we call contention based access method with carrier sense multiple access collision detection. So if you are using legacy, then automatically the carrier sense multiple access collision detection is used to detect and then to decide how, in case multiple communications are detected. So with Ethernet LAN of today, they use what you call switch that operates in full duplex. Full duplex communication with Ethernet switches do not require access control through carrier sense multiple access collision detection, because a switch itself, it's an intelligent device. It can send and receive at the same time or simultaneously. So Ethernet frame fields, we need to look at the maximum Ethernet size, which is 64 bytes, and then the maximum it's 1518. So the preamble field, what we call the preamble, this one here, is not included or is not part of the frame, or it is not used to describe the size of the frame. So any frame that is less than, because you're saying, yeah, it is 64 up to 1518. So anything that is less than 64 in length, it is considered as collision fragment or ranch frame, and is automatically discarded. Frames with more than 500, 500, sorry, not 1500 bytes of the data are considered as jumbo. So if it exceeds the 500, it is considered as jumbo or the giant frames. So if the size of the transmitted frame is less than the minimum or greater than the minimum, then there is frame, because it does not meet the requirement size. Then dropped frames are likely to be a result of collision or other unwanted signals. They can be considered invalid. Jumbo frames are usually supported by most jumbo, because the jumbo, that is when it is greater. That is if it is greater than the maximum size. So most of the time it is supported by fast Ethernet, gigabit Ethernet switch. If those devices have issues, then they will help in generating that type of error. So here use Wireshark to examine Ethernet frame. Use Wireshark to examine Ethernet frames. Part 1, examine header fields in Ethernet 2, and then capture and analyze Ethernet frame. Ethernet MAC addresses. An Ethernet MAC address consists of 48 bits binary value expressed in 12 hexadecimal value. The good thing, you've covered IPv6. So given that 8 bits, the 8 bits are equivalent to 1 byte, is a common binary grouping. So binary, this range from 00 to 11 can be represented in hexadecimal. So if that be represented in hexadecimal, they will be divided 8 divided into 2, and then at the end of the day you get this 00 and then up to FF. So here we have a 0 hexadecimal. This is a 0 hexadecimal, an hexadecimal, and then that's the range, can be represented in that. So when using hexadecimal, the leading zeros are always displayed. They are always displayed to complete 8 bits representation. For example, binary with this, because this one here it is a 2 and a 4H, indicating that it is a 10. So this is a 10. So it's represented in hexadecimal as this. So in case, let's say I have 1, 0, 1, 0, like this. If I convert it, I'll get 10. But in hexadecimal, it will be A. Since the MAC addresses, it has to be represented in this hexadecimal as range of from 00 up to FF. And here we have A, then automatically I will add a 0 here to indicate that this is, there is another value. There is another value to make it complete. Hexadecimal numbers are often represented by value preceded by this EG073 to distinguish between decimal and hexadecimal value in the documentation. What does this mean? That if I write something, I'm dealing with hexadecimal and I have 73 here, someone will interpret this as maybe 73. If I have maybe 100 like this, someone will come and treat it as 100. 100. So to distinguish hexadecimal from decimal digits or numbers, if, for example, I have something like 80, whereby this one here you can either confuse it as decimal or hexadecimal, I can proceed precede as 0, something like this. So automatically this, it will indicate that it's an hexadecimal number. Or you can write it as 80 with H, as you're seeing this, as this. So in those scenarios where you'll find like it's this and here it's self-explanatory, but those ones, for example, this. So if the context is not clear, then we can go ahead and add something like H or 0, 100, like this. So still under Ethernet MAC address. In Ethernet LAN, every network device, whether you want or not, is connected. Every network device is connected to the same shared media. In an Ethernet LAN, every network device is connected to the same shared media. So the MAC address provides a method for device identification and data link layer of the OS at the data link layer of the OSI model. So an Ethernet MAC address, which we said that it's a 48-bit address expressed in 12 hexadecimal digits. Because a byte is equivalent to 8 bits, we can also say that the MAC address is 6 bytes. Because now if you are saying the 6, we expect 8, 12 hexadecimal. 12 hexadecimal. So there will be 8 here, H, H. So these are actually, we are saying 6 bytes. So if there are 6 bytes, 1, 2, 3, 4, 5, then 6. So with the 6 bytes, so here we expect 4, 4, then 4, 4, then 4, 4. This side still 4, 4, 4, 4, 4. So in other words, while we're saying 8, we expect 2, something like 0, 0, 0, then 0, 0. 0, 0, 0, 0, then 0, 0, like this. So these are 6, 1, 2, 3, 4, 5, 6. So there are 6 there are 6 bytes in length. So all MAC addresses must be unique to the Ethernet device or Ethernet interface. So to ensure this, all vendors that sell Ethernet devices must register with IEEE to obtain unique 6 hexadecimal, for example, 24 bytes. So the 24 bytes, that is, sorry, 24 bits, this. So all vendors, they have to register with IEEE so that they can get the unique number that identifies that very organization. Yeah? And those are the equivalent to 24 bits or 3 bytes codes called organization unique identifier. Then the Ethernet MAC address consists of 6 hexadecimal vendor code followed by 6 hexadecimal vendor assigned value. So the vendor assigned value now it's the 6 the 6 sorry, the 3 bytes 3 bytes that uniquely identifies a device. So we have 6, these, and the so-called 6 by for organization unique identifier, and then vendor assigned. So this one here, it uniquely identifies, it uniquely identifies the vendor, this part, 3 bytes. Then the other 3 bytes are assigned by the vendor to a specific computer to uniquely identify a computer manufactured by that vendor. So frame processing, when a device is forwarding a message to an Ethernet network, the Ethernet header includes the source and destination MAC address. So when the network interface receives an Ethernet frame, it examines the destination MAC address to see if it matches the physical MAC address that is stored in RAM. If there is no match, then the device discards the frame. If there is a match, it passes the frame up the OSI layers where the encapsulation process takes place. So in that process, when our device receives, when it receives the MAC address, then the source MAC address, remember the frame, once a destination receives a frame, the frame it contains the source and destination MAC addresses. So the receiver will have to compare the destination MAC address together with the MAC address that is assigned to that very physical network interface card. In case there is a match, it will be passed to the upper layers of the OSI or in the OSI layers so that it can be processed. But if there is no match, the destination MAC address in the frame and then the MAC address on the network interface card, then that frame is going to be discarded. Note, Ethernet network interface card also accepts frames if the destination MAC address is the broadcast. So even if there is no match, as long as it's a broadcast, then it will be the broadcast or multicast that will be accepted. So any device that is the source or destination of the Ethernet frame will have an Ethernet network interface card and therefore the MAC address. And therefore the MAC address. So any device that is the source or destination of the Ethernet frame will have what we call network interface card, and once there is a network interface card, then we expect the MAC address. This includes workstations, servers, printers, mobile devices, routers, anything that is called a network, network device. It has to have the network interface, either it can be wireless, and as long as it's a card, network interface card, it will have to have the MAC address. We have what you call the unicast MAC address in that process. Actually, you expect the unicast, then multicast, and then the broadcast. So in Ethernet, different MAC addresses are used in layer 2, unicast, broadcast, and then the multicast communication. So with unicast MAC address, it is a unique address that is used when a frame is set from a single transmitting device to a single destination device. So the process that the process the process that a source host uses to determine the destination MAC address associated with IPv4 is known as what we call address resolution protocol. We're going to cover this in chapter 9, I think. So the process that a source host uses to determine the destination MAC address associated with an IPv4 address is called, IPv6 is called neighbor discovery. So note, the source MAC address must always be unicast. So the source, it will always be a single, but the destination can be single, that is what we call the still unicast, one-to-one, or can be multicast, it's one to a group, or one to entire network, that is the broadcast. Broadcast MAC address, Ethernet broadcast frame is received and processed by every device on an Ethernet LAN. The features of the Ethernet broadcast are as follows. It has the destination MAC address of the entire network. It's FFFF in hexadecimal. So in other words, that all the 48 bits are ones in binary. It is flooded out all the Ethernet switch port except the incoming port. It is not forwarded by the router. So a router, it cannot forward a broadcast message. And if the broadcast message is sent, it is forwarded on to all the active interfaces on the network except the incoming port. So the incoming port, as you can see, it is this one here, that all these they will receive, but this one here, it is the incoming port. That's the reason why you're not seeing the arrow, because it's the one that feeded that was used to feed the switch. So if the encapsulated data is an IPv4 broadcast packet, this means that the packet contains a destination IP address that has all ones in the host portion. Now this time you know what we call the broadcast address. So if the broadcast, if we are dealing with IPv4 and the broadcast MAC address, it is the broadcast MAC address. The broadcast MAC address is FF slout. Then the broadcast IP address, it will always be the ones, as you can see, that the destination IP address that has all ones in the host portion. In the host portion. So as you do the reading, you'll get to know what it means here. So this numbering in the address means that all hosts on that local network will receive and process the package. This numbering or the addressing means that all hosts on the local network will receive and then process the package. Then we have what you call the multicast. So Ethernet multicast frame is received um, is received and processed by a group of devices that belong to the same multicast group. There is a destination MAC address of this 01005. It's a must. It has to begin with this for multicast. So when the encapsulated data is an IPv4 multicast packet and the destination MAC address and then the destination MAC address as 33 when the encapsulated data is IPv6. So when it's IPv6, then the MAC address, it will be in this format 333, and then in IPv4. So there are other reserved multicast destination MAC addresses for when the encapsulated data is not IP, such as spanning tree protocol, and still it is flooded out all Ethernet switch port except the incoming port, unless the switch is configured for multicast snooping. For multicast snooping, it is not forwarded by the router still, unless the router is configured to route multicast package. So because multicast address represents a group of addresses, sometimes called host group, they can only be used as the destination of the packet, but not the source. So the source will always be unicast again. So as with the unicast and broadcast address, the multicast addresses or address require corresponding MAC address. That the multicast IP address requires a corresponding multicast MAC addresses. So Here is the lab where we have to view. You viewed network device MAC addresses, and this part one, set up a topology and initialize devices, configure devices, and verify connectivity, display, describe, analyze the MAC address, the MAC addresses. So MAC address table. So with the switch fundamentals, a layer two Ethernet switch uses what you call layer 2 MAC addresses to make forwarding decision. It is completely unaware of the data. It is completely unaware of the data or the protocol being carried in the data portion of the frame, such as IPv4 packets and address resolution protocol message or IPv6 neighbor discovery packet. So the switch makes its forwarding decision based on the layer 2 MAC address. It uses the MAC addresses to do the forwarding mechanism. So an Ethernet switch examines its MAC address table to make forwarding decision for each frame, unlike legacy Ethernet hubs that repeat bits out of all ports except incoming port. But when a switch is turned on, most of the time the MAC address table is empty. So the MAC address table sometimes referred as content addressable memory, or you can call it CAM. So switch learning and then forwarding. So examine the source MAC address, examining the source MAC address, that is LAN, that process called learning. So every frame that enters a switch is checked for the new information to learn. It does this by examining the source MAC address of the frame and the port number where the frame entered the switch. So if the source MAC address does not exist, it is added in the table along with the incoming port number. So if the source MAC address does exist, that it already exists, then the switch updates the refresh timer for the entry. So by default, most of the Ethernet switch keeps an entry in the table for 5 minutes. But every time it receives, then the timer is refreshed. So the switch, it builds its MAC address table based on the source MAC address or the source device. So once the source device sends frame into the switch, then the frame it is examined to see the source MAC address. If the source MAC address does exist, then the timer is the one that refreshed. If the MAC address doesn't exist, then it is captured along with the port number. Note that the source MAC address does exist in the table, but on a different port. The source, if the source MAC address does exist in the table, but on a different port, then the switch treats this as a new entry, and the entry is replaced using the same MAC address, but with more current port number. So if the MAC address 1 is recorded with F01, and then you decide to connect this cable, this computer, to FA010, then the MAC address is going to remain, but the port number is going to be replaced now from 0 to more current port number, which is a 10. Then find the destination MAC address. Remember this previous one, it was learning. Now the switch is learning the MAC address. Now the switch, it has to find the destination MAC address. Now the MAC address table, maybe 1, 2, 3, 4, they are listed in the MAC address table. Every time a switch receives, it has to update. But if it wants to forward, then it has to find the MAC address among these MAC address MAC addresses in the MAC address table. There is no any other special table where to find the destination MAC address, but it's a single MAC address table. We have 1, 2, 3, that every time a switch receives a frame, it will have to check the source MAC address. Is it listed here? So if it's not listed, it is listed there. Now it's time to forward. Now the switch, it will check among these known MAC addresses to see if the destination MAC address is known. So if it's not known, then automatically there is another mechanism to find that MAC address. So if the destination MAC address is unicast address, then the switch will look for the match between the destination MAC address of the frame and an entry in its MAC address table. So if the destination MAC address is in the table, then it will forward the frame out of specified port. If the destination MAC address is not in the table, then the switch will forward the frame out of all ports except incoming port. This is called unknown unicast. So if it's unknown unicast, then the source MAC address which will be captured, but the destination MAC address is unknown. So it is treated as unknown unicast. And the switch, it has to forward that unknown unicast onto all active ports except the incoming port. Note, if the destination MAC address is a broadcast, then all multicast or a multicast, then the frame is also flooded out. So if it's unknown unicast, it is flooded out of all ports. If it's multicast or broadcast, still it is flooded out of all ports except incoming port. So filtering a frame, as a switch receives frames from different devices, it is able to populate its MAC address table by examining the source MAC address of every frame. So when the MAC address table of a switch contains the destination address, then it is able to filter the frame and then forwards it out of the single port. So if the MAC address that exists, the destination MAC address that exists, there is no need of flooding. It will have to filter and look for specific or specified IP MAC address, destination MAC address, and then forwards a frame out of a single port. So this is a video where you have to play. This will cover the following: how switch builds the MAC address, how switch forwards frame based on content of their MAC address table. Still, this is the video what a switch does when a destination MAC address, this is supposed to be MAC, not AMC, when a MAC address is not listed in the switch's MAC address table. So what will happen? Flooding that frame out of all ports except the incoming port. Then what a switch does when the source MAC address, this is MAC address, is not listed in the switch's MAC address table. What a switch does when the source, this is when the destination, when the source MAC address is not listed. Okay, then we have the lab. View the switch MAC address table. So build and then configure the network, then examine switch MAC address table. So switch speed, have what you call switch speeds and then forwarding methods. Switch speeds and then forwarding methods. So switches use one of the following forwarding methods, where we have store and forward switching and then cut through. So store and forward, the frame forwarding, this is a frame forwarding method that receives the entire frame and computes what you call cyclic redundant cycle. If the CRC is valid, if the CRS is valid, then the switch looks up the destination address. It finds it tries to locate the destination address, which determines the outgoing interface. So once the MAC address, the destination MAC address is known, then it determines the outgoing interface, and then the frame is forwarded out of the collect port. That is if the frame is valid. Cut-through switching, this is a frame forwarding method uh, that forwards a frame before it entirely received. Before that frame, it is entirely received or completely received. So at a minimum, the destination address of the frame must be read before the frame can be forwarded. So once the destination MAC address is known, then it won't wait for the complete frame to be received and then saved. So a big advantage of store and forward switch is that it determines if the frame has error before propagating the frame. So when an error is detected in a frame, then the switch discards the frame. So discarding frame with errors reduce the amount of bandwidth. So discarding frames with errors reduces the amount of bandwidth consumed by corrupt error. So store and forward switching is required for quality of service analysis on converged network when where the frame classification for traffic prioritization is necessary. For example, voice over IP data streams needs to have priority over web browsing um, traffic. So within the cut-through switching, the switch acts upon the data as soon as it is received. Even if the transmission is not complete, the switch buffers just enough of the frame to read the destination MAC address, because once it reads the destination MAC address, then it can determine to which port it should forward out the data. So this switch, the switch does not perform any error checking on the frame. So with cut-through, there is no need of performing an error checking. So there are two types of variants of cut-through switch. So within cut-through, there are other types of or other modes. We have fast forwarding switch. It offers lowest level of latency by immediately forwarding the packet after reading the destination address, because the fast forwarding switching starts forwarding before the entire packets have been received. There may be times when the packets are relayed with errors. The destination network interface card the network interface card discards the faulty packets upon recipient. So fast forwarding switch is the typical cut-through. So when you can fast forwarding switching, it's a typical cut-through switching. That's right. It will actually read, look at the halfway of the frame, and once it reads the destination MAC address, then automatically it will forward that. In case, let's say there are errors within the frame, there will be, or the frame, it will be discarded or dropped by the destination. So it's the role of the destination now to check whether the received frame is valid or invalid. When it comes to fragment-free switching, for fragment switch, a compromise between the highest line latency and high integrity of store and forward switch and the low latency and reduced integrity of fast forwarding switch. The switch stores and performs an error checks on 64. So the fragment free to check with the fragment free switching. So the switch stores and performs error check on a first 64, the first 64 bytes of the frame before forwarding, because most of the network errors and then the collision, they do occur during the first 64 bytes. So this ensures that collision has not occurred before forwarding the frame. So once it receives the 64, that is fragment-free switching. Once it receives 64 bits, then those 64 bits are checked to in case there are errors, in case there are network errors or the collisions before it forwards the frame. So memory buffering on a switch, the methods, we have port-based memory and then the shared. So Ethernet switch may use buffering technique to store frames before forwarding them, or when the destination port is busy because of the congestion. So they have to be buffered or stored temporarily as uh, uh, some resources are getting released. So port-based memory frames are stored in queues that are linked to specific incoming and outgoing port. So a frame is transmitted to the outgoing port only when all the frames ahead in the queue have been successfully transmitted. It is possible for a single frame to delay the transmission of all the frames in a memory because of busy destination port. This delay occurs even if the other frames could be transmitted to open destination. So we have even the shared memory deposits all the frame. It's a repository of all frames into a common memory buffer shared by all switch ports. So now the shared memory is the memory for the entire switch. So the frame in the buffer are dynamically linked to the destination port, enabling packets to be received on one port and then transmitted on another port, received on one port and then transmitted on another port without moving it to different queues. So we have duplex and then speed settings. So two of the most basic settings on a switch are the bandwidth. At bandwidth, it's the speed and then duplex setting for each individual switch port. So it is critical that duplex and then bandwidth settings match between the switch port and then connected devices. So there are two types of duplex settings where we have half and then full and half. So full, both ends of the connection can send and receive simultaneously. Only one end of the connection can send at a time, that is in half duplex. So auto negotiation is an optional function found on most of Ethernet switches and network interface card. It enables two devices to automatically negotiate the best speed and then duplex capability. Note, gigabit Ethernet port only operates in full duplex. Giga in full duplex. So duplex mismatch is one of the most common causes of performance. Duplex mismatch is one of the most common causes of the performance issue on 10 stroke 100 MB per second Ethernet link. It occurs when one port of the link operates at half duplex while other port operates in full. So this can occur when one or both of ports are reset and the auto negotiation process does not uh, result in both link partners having the same configuration. Can also occur when you configure one side of the link and forgets to configure the other one. So both sides of the link should have auto negotiation on, or both sides should have it off, because best practice is to configure both Ethernet switch to operate in full duplex. So in case, let's say we have full duplex, half duplex, we expect fire in between. We have what you call auto, MDIX. Connection between device once required the use of either crossover or straight through cable. The type of cable required depended on the type of interconnecting device. Note, a direct connection between router and the host requires this. Note, you need to note this, that note, a direct connection between a router and a host we have a router and then the host. The host, this cable, it has to be across over cable. So most switches now supports automatic media dependent interference crossover feature. So when enabled, the switch automatically detects the type of cable attached to the port and configures that interface accordingly. So the auto MDIX feature is enabled by default on switches running Cisco IOS released by this version 12 or 18 series and later. However, the feature could be disabled. You can disable it. For this reason, you should always use the correct cable type and not rely on the auto MDIXL. So if in case, let's say it is disabled, then you have to use the correct type of the cable. The correct type of the cable, if the devices are the same, you use crossover. If they are different, you use straight through. So MDIX can be re-enabled using this MDIX, then auto on an interface configuration command or prompt. So you call an interface and then run that command. So that marks the end of our module.